Hello there, and welcome back to this quiet corner where time moves slowly and curiosity needs no deadline. Tonight, we're stepping into water. Not the oceans you know, with their familiar shapes and coastlines traced on modern maps, but an ocean from a world so distant it seems almost like a dream. We're travelling to a time when vast reptiles, not whales, ruled the depths, when strange coiled shells drifted through waters warmer than any sea today, and when the very chemistry of the ocean itself was different, stranger, and in some places deadly. This is the deep sea during the age of dinosaurs. It's a world where the rules were written differently, where the waters held secrets we're only now beginning to understand, and while dinosaurs walked the land above beneath the waves, an entirely different empire thrived in the blue. Before we begin, settle in. Let the world outside fade for a moment. There's no need to keep track of time here because the story we're about to tell unfolded over more than 180 million years. It's a story told in stone and fossil, in layers of ancient seabed now pushed high into mountains, and in the faint chemical traces left behind in rock, formed from mud that settled in seas long vanished. It's a story of warmth and depth, of creatures both familiar and alien, and of an ocean that stretched across a world we would not recognize. The age of dinosaurs is a phrase that brings to mind towering reptiles on land. But for every Tyrannosaurus that stalked ancient forests, for every herd of long-necked sauropods that grazed under Jurassic skies, there was an ocean teeming with life just as diverse, just as strange, and in many ways, just as powerful. While we often look up at dinosaur skeletons in museums, we rarely stop to imagine what swam beneath them, in waters that covered more of the planet than they do today. Tonight, we're diving down, and we're staying there. The age we're stepping into is called the Mesozoic era. It spans three great periods: the Triassic, the Jurassic, and the Cretaceous. Together they stretch from about 252 million years ago to 66 million years ago, when an asteroid brought it all to a sudden, violent end. But for the 186 million years in between, the Earth was a greenhouse world, a planet without polar ice caps, where palm trees grew in what is now Alaska, and where the oceans were not cold at the bottom but warm, sluggish, and rich with life in ways we can barely imagine. Picture yourself standing on the shore of a Cretaceous sea. The air is thick with moisture, heavy and warm. The water lapping at your feet is not the cool, clear blue of a modern beach. It's warmer, perhaps as warm as bath water. And if you were to wade out and dive beneath the surface, you would find that the warmth doesn't disappear as you descend. In today's oceans, the water grows cold quickly as you go deeper, but in the Mesozoic, the temperature dropped much more gradually. The deep ocean, thousands of meters down, was not near freezing as it is now. It was perhaps 15 to 20 degrees warmer, warm enough that the very chemistry of the water, the way oxygen moved through it, the way nutrients cycled, was fundamentally different. The continents themselves were scattered differently across the globe. North America and Europe were just beginning to separate, forming the early Atlantic Ocean, which was little more than a narrow seaway compared to the vast expanse it would become. South America and Africa were still joined, as were India, Antarctica, and Australia. The Tethys Ocean, a vast tropical sea, stretched east to west across the middle of the world, separating the northern and southern land masses, and to the west, the Pacific, or what geologists call Panthalassa, the all-ocean, dominated the globe, covering more than half the planet's surface in unbroken blue. This was a world of shallow seas as well. Because the oceans were warmer, and because the seafloor was younger and sat higher, sea levels rose dramatically. Water flooded across the continents, creating vast shallow seas where deserts and plains exist today. In North America, the western interior Seaway split the continent in two, stretching from the Arctic to the Gulf of Mexico. Europe was an archipelago of islands scattered across warm, shallow waters, and across these sunlit seas, life exploded in forms both beautiful and bizarre. But we're not staying in the shallows tonight. We're going deeper, into the places where light fades, where pressure builds, and where the true strangeness of the Mesozoic ocean reveals itself. Because while the shallow seas are well studied, well documented in fossil beds rich with ammonites and ancient clams, the deep sea of that time remains more mysterious. We know it was there, we know it was different. And through careful study of sediments, of isotopes locked in ancient shells, and of the rare fossils that made their way from the abyss to shallower waters, we can begin to piece together what it might have been like. So let's begin the descent. The sun is shining on the surface, the water is clear and warm, and somewhere far below, in depths where no sunlight has ever reached, the ancient ocean is waiting. The world of the Mesozoic was not a single static moment, but a long, slow evolution spanning 3 distinct periods. Each brought its own character to the oceans, its own creatures, and its own particular set of conditions that shaped life beneath the waves. To understand the deep sea of this time, we first need to understand the broader picture of what the Earth itself was like during these ages. The Mesozoic era began in the aftermath of the greatest extinction event in Earth's history. The Permian extinction, which occurred at the boundary between the Paleozoic and Mesozoic, wiped out more than 90% of marine species. The oceans were left devastated, their ecosystem shattered, but life, as it always does, found a way forward. The Triassic period, the first chapter of the Mesozoic, was a time of slow recovery. The supercontinent Pangaea still dominated the globe, a single massive landmass surrounded by the vast Panthalassa Ocean. The climate was hot and dry in the interior of the continent, but along the coasts and in the growing Tethys Sea, life began to rebuild. In the oceans, the survivors of the extinction began to diversify. Early marine reptiles descended from land-dwelling ancestors tentatively returned to the sea. Ichthyosaurs, dolphin-shaped predators with large eyes and streamlined bodies, appeared and quickly became successful hunters. Ammonoids, close relatives of the Ammonites, had been nearly wiped out, but the few species that survived began to radiate into new forms. Coral reefs, which had been devastated, slowly began to recover, though it would take millions of years for them to regain their former glory. The Triassic Ocean was warm, but not as warm as it would become. The deep sea was less well oxygenated than in earlier times, a condition that would persist and even worsen in the periods to come. But life adapted. Filter feeders, burrowing creatures, and swimming predators all found their niches. By the end of the Triassic, the stage was set for the great diversification that would define the Jurassic, and then came the Jurassic, perhaps the most iconic of the 3 periods. It was during the Jurassic that Pangaea began to break apart in earnest. The Atlantic Ocean, which had been a narrow rift, began to widen. The Tethys Sea grew larger, its warm waters spreading across the equatorial belt. Sea levels rose dramatically, flooding low-lying areas of the continents and creating vast shallow seas. The climate grew even warmer. There were no ice caps at the poles. Palm trees and cycads grew in high latitudes. And in the oceans, life flourished. Plesiosaurs with their long necks and paddle-shaped flippers became some of the most successful marine predators. Ammonites reached their peak diversity, their coiled shells filling the water column at every depth. Rudist clams, strange bivalves with asymmetrical shells, began to build reefs that would eventually rival those of corals. And in the deeper waters, creatures we know almost nothing about moved through the darkness, leaving behind only the faintest traces of their existence. The Jurassic Ocean was a place of abundance. The warm temperatures and high sea levels meant that nutrients were constantly being cycled from the land into the sea. River runoff carried minerals and organic matter into coastal waters, feeding vast blooms of plankton. These, in turn, supported huge populations of fish, squid, and the predators that hunted them. It was an ocean in balance, productive and thriving. But then came the Cretaceous, the final and longest period of the Mesozoic. The Cretaceous was a time of extremes. Sea levels rose to heights not seen before or since, flooding more than 40% more land than is flooded today. The climate grew even hotter, and the oceans, already warm, became warmer still. Deep ocean temperatures reached levels that seem almost unimaginable to us now, perhaps as high as 15 to 20 degrees Celsius, compared to the near-freezing temperatures of today's abyss. The Cretaceous was also a time of massive volcanic activity. Large igneous provinces, vast outpourings of lava that covered areas the size of continents, erupted multiple times during the period. These eruptions released enormous quantities of carbon dioxide into the atmosphere, driving global warming to even greater extremes. They also released sulfur and other gases that affected ocean chemistry, sometimes triggering what are known as oceanic anoxic events, times when large expanses of the ocean lost most or all of their dissolved oxygen, creating dead zones where little could survive. Yet for all its challenges, the Cretaceous was also a time of incredible diversity. Mosasaurs, giant marine lizards, appeared and quickly became the apex predators of their time. Ammonites evolved into an astonishing variety of shapes and sizes, from tiny coiled shells no bigger than a coin to giants measuring 2 meters across. Rudist reefs spread across the tropical seas, creating complex ecosystems that rivaled anything seen before or since. And in the depths, life continued to adapt to conditions that grew ever more extreme. This was the world of the Mesozoic ocean, a world of warmth and abundance, but also of danger and volatility. A world where the rules were different, where the chemistry of the water itself could shift dramatically, and where life was constantly tested by a planet that seemed determined to push it to its limits. And through it all, in the sunlit shallows and the dark abyss alike, life endured, evolved, and thrived in ways that shaped the oceans we know today. One of the most striking features of the Mesozoic ocean was its temperature. If you could step into a time machine and dive into the seas of the Cretaceous or Jurassic, the first thing you would notice, even before you saw the strange creatures or the different chemistry, would be the warmth. The water would feel almost tropical everywhere you went, from the equator to the poles, from the surface down to depths of several thousand meters. This was a greenhouse world, and the oceans absorbed and held that heat in ways that fundamentally changed how they functioned. In today's oceans, there is a sharp divide between the warm surface layer and the cold deep water. This boundary, called the thermocline, is like an invisible wall. Above it, the water is mixed by winds and waves, warmed by the sun and teeming with life. Below it, the water is cold, dark, and still. But in the Mesozoic, this divide was much less pronounced. The thermocline was weaker, shallower, and less stable. Warm water extended, far deeper than it does today, and the temperature gradient was gentler. Why was the ocean so warm? The answer lies in a combination of factors. First, the climate itself was much hotter. Carbon dioxide levels in the atmosphere were several times higher than they are today, perhaps as much as 4 to 6 times higher during some parts of the Cretaceous. This greenhouse effect trapped heat, raising global temperatures by perhaps 10 to 15 degrees Celsius compared to the present day. There were no ice caps at the poles to reflect sunlight back into space. Instead, the polar regions were covered in forests and shallow seas that absorbed heat. Second, the configuration of the continents affected ocean circulation. Today, cold water forms at the poles and sinks, driving a global conveyor belt of deep ocean currents that distribute cold water throughout the world's oceans. But in the Mesozoic, with no polar ice and warmer temperatures everywhere, this process was much weaker. Deep water formation still occurred, but the water that sank was not nearly as cold. It carried its warmth with it into the depths, creating a deep ocean that was far warmer than anything we know today. Third, the oceans themselves were higher. Sea level during the Cretaceous was perhaps 100 to 200 meters higher than it is now. This was partly due to the lack of ice caps, which meant more water was in liquid form rather than locked up in glaciers. But it was also due to something called thermal expansion. Warmer water takes up more volume than cold water, and with the entire ocean warmer from top to bottom, the seas swelled, flooding across the continents and creating vast shallow seas. These shallow seas played a crucial role in the Mesozoic ocean system. They were warm, sunlit, and incredibly productive. They acted as nurseries for fish and invertebrates, as feeding grounds for marine reptiles, and as factories for carbonate production. The shells of countless trillions of tiny organisms, from plankton to clams to corals, accumulated on the seafloor, forming the thick layers of limestone and chalk that we see today in formations like the White Cliffs of Dover. But the warmth had consequences. Warmer water holds less dissolved oxygen than cold water. This is a simple fact of chemistry, and it had profound effects on life in the Mesozoic ocean. The surface waters, mixed by winds and waves and exposed to the atmosphere, were still well oxygenated. But deeper down, where mixing was weaker, and where organic matter sinking from above consumed oxygen as it decayed, oxygen levels dropped. In some places and at some times they dropped to near zero, creating anoxic zones where almost nothing could live. These anoxic zones were not constant. They came and went, sometimes persisting for thousands of years, sometimes disappearing just as quickly. They were driven by a combination of factors. volcanic eruptions that released nutrients and triggered massive plankton blooms, changes in ocean circulation that reduced mixing, and the sheer warmth of the water itself. When conditions were right, or perhaps wrong, vast expanses of the ocean would turn into dead zones. The evidence for this is found in black shales, organic-rich sediments that formed in oxygen-depleted waters where dead organisms could not fully decompose. These black shales are found around the world, in rocks of Jurassic and Cretaceous age, silent witnesses to a time when the ocean's chemistry could shift dramatically. Yet life persisted. Some organisms adapted to low oxygen conditions. Others migrated following the currents and the oxygen to places where they could survive. And when the Anoxic events ended, as they always did, life returned, recolonizing the dead zones and rebuilding the ecosystems that had been lost. The Mesozoic ocean was a place of resilience as much as it was a place of challenge. The higher sea levels also created something that no longer exists. Today, vast epicontinental seas. These were not true oceans, but shallow seas that flooded across the continents, creating seaways that could stretch for thousands of kilometers. The Western Interior Seaway in North America is perhaps the most famous example. During the late Cretaceous, it split North America in two, running from the Arctic Ocean down through what is now Canada and the United States, all the way to the Gulf of Mexico. At its widest, it was perhaps 1,000 kilometers across. At its deepest, it was perhaps only a few hundred meters deep, far shallower than the true ocean basins. These epicontinental seas were strange places. They were warm, shallow, and productive, but they were also volatile. Changes in sea level, even small ones, could flood or drain vast areas. Changes in climate could alter the temperature and salinity of the water, affecting the creatures that lived there. And because they were connected to the open ocean, they served as highways for marine life, allowing creatures to migrate between regions that would otherwise be separated by land. The creatures that lived in these seas were a mix of open ocean species and those adapted to shallow water. Ammonites drifted in the water column, their shells buoyed by gas-filled chambers. Fish, both ancient lineages and the newly evolved teleosts with their mobile jaws, hunted in schools. Marine reptiles, from the small mosasaurs to the massive plesiosaurs, prowled the depths, hunting for prey. And on the seafloor, clams, snails and sea urchins grazed and filtered the water, building the thick layers of sediment that would one day become rock. The Mesozoic ocean was a warmer, higher, and in many ways stranger place than the oceans we know. It was an ocean where the deep sea was not a cold, dark abyss, but a warm, sluggish realm. It was an ocean where vast, shallow seas spread across the continents, creating habitats that no longer exist. And it was an ocean where life, for all its abundance, was constantly tested by a chemistry that could turn deadly without warning. Yet through it all, life endured, adapted and flourished, filling every niche, every depth, and every corner of this ancient blue world. While the deep ocean holds a particular mystery and allure, the shallow seas of the Mesozoic were where most of the action took place. These were not the deep abyssal plains, but the sunlit waters that flooded across the continents, creating vast seaways and shallow coastal regions that stretched for hundreds and sometimes thousands of kilometers. These epicontinental seas were some of the most productive and diverse habitats on Earth during the age of dinosaurs, and understanding them helps us understand the ocean as a whole. The Western Interior Seaway is perhaps the best studied example of these ancient seas, and for good reason. During the late Cretaceous, from about 100 million to 66 million years ago, this seaway divided North America into two land masses, Larimedia to the west and Appalachia to the east. The seaway stretched from the Arctic to the Gulf of Mexico, a distance of more than 3,000 kilometers. At its widest, during the high stand of sea level around 90 million years ago, it was perhaps 1,000 kilometers wide, but despite its size, it was shallow. Most of it was less than 200 meters deep, and large areas were less than 100 meters deep. This shallowness had profound effects. The water was warm, heated by the sun throughout its entire depth. There was no cold, dark bottom here, no thermocline to separate surface from deep. Instead, the entire water column was mixed and oxygenated, at least when conditions were favourable. Sunlight penetrated to the seafloor in many places, allowing seagrasses and algae to grow. And the combination of warmth, sunlight and nutrients washed in from the surrounding lands created conditions for explosive productivity. The seafloor of the western, interior Seaway was a layer cake of mud, sand and shells. Rivers draining the rising Rocky Mountains to the west carried sediment into the sea, creating deltas and mud flats along the western shore. The eastern shore, by contrast, was low and swampy, with fewer rivers but extensive wetlands that released organic matter into the water. And in between, in the open water, plankton bloomed in vast numbers, their tiny shells raining down to the bottom like snow. The creatures that lived in this seaway were a mix of familiar and alien. Ammonites, those iconic spiral-shelled cephalopods, were everywhere. Some species were tiny, no bigger than a coin. Others grew to enormous sizes, their shells measuring a meter or more across. They drifted through the water column, using their tentacles to catch small prey and their gas-filled chambers to control their buoyancy. They were the equivalents of squid and octopuses today, but with external shells that preserved beautifully as fossils. Fish filled the waters as well. There were ancient lineages like the sturgeon-like pycnodontids, with their crushing teeth for eating shellfish. There were early sharks, not yet the sleek predators we know today, but stockier, slower forms with broad fins. And there were the teleosts, the ancestors of most modern fish, which had just appeared and were beginning to diversify. These fish had a new innovation: mobile jaws that could open wide and snap shut, making them far more effective predators than their ancestors. But the true rulers of the western interior Seaway, and of the Mesozoic seas in general, were the marine reptiles. These were not dinosaurs, despite common misconceptions. Dinosaurs were land animals, but their relatives, creatures that had returned to the sea from land-dwelling ancestors, filled every niche in the ocean, and nowhere were they more diverse or more abundant than in the shallow seas. Mosasaurs were perhaps the most fearsome. These were giant lizards, relatives of modern monitor lizards and snakes that had adapted to a fully aquatic lifestyle. They ranged in size from a few meters to more than 15 meters long. They had streamlined bodies, paddle-like limbs, and powerful tails that propelled them through the water. Their jaws were lined with sharp, recurved teeth, perfect for gripping slippery prey. And they were everywhere, from the surface to the bottom, hunting fish, ammonites, other mosasaurs, and even seabirds that ventured too close to the water. Plesiosaurs were another major group. These reptiles had 4 paddle-shaped flippers and either long necks with small heads or short necks with massive heads, depending on the species. The long-necked forms, like Elasmosaurus, were probably ambush predators, using their necks to strike quickly at passing fish. The short-necked forms, the pliosaurs, were more like modern orcas, fast and powerful hunters that could take down large prey. And then there were the sea turtles, already recognizable as relatives of modern turtles but often much larger. Some species, like Archelon, had shells measuring more than 4 meters across. They grazed on seagrass and jellyfish, their beaked mouths perfectly adapted for this diet. They nested on beaches, laying their eggs in the sand just as sea turtles do today, creating a link between the ancient world and the present. The shallow seas were not just hunting grounds, but nurseries. Many species of fish and reptiles gave birth to live young or laid their eggs in protected coastal areas. The young would spend their early lives in the shallows, feeding and growing before venturing out into the open ocean. This pattern, seen in many marine animals today, was already well established in the Mesozoic. But the western interior Seaway, like all epicontinental seas, was a fragile environment. Sea level fluctuated over time, driven by changes in the volume of ocean water and the height of the seafloor. When sea level rose, the Seaway deepened and widened, providing more habitat. But when sea level fell, the Seaway shrank and in some cases disappeared entirely, draining away and leaving behind dry land. These fluctuations happened over hundreds of thousands to millions of years, but they had profound effects on the creatures that lived there. Species that depended on the Seaway had to migrate or adapt, and many did not survive. The sediments deposited in the western interior Seaway tell this story in layers. Dark shales indicate times when the water was deep and poorly oxygenated. Limestones and chalks indicate times when plankton bloomed and their shells accumulated in vast numbers. Sandstones indicate times when rivers brought sediment from the land, or when storms churned the seafloor. Each layer is a snapshot of a moment in time, a record of the conditions that existed and the life that thrived or struggled under those conditions. Today, the western interior seaway is gone, drained away as sea levels fell and the continents rose, but its legacy remains. The rocks it left behind stretch across the Great Plains of North America, forming cliffs, buttes, and badlands. Fossils erode out of these rocks constantly, revealing the creatures that swam in those ancient waters. And by studying these fossils and the rocks that contain them, we can reconstruct not just what lived in the seaway, but how the entire ecosystem functioned, how it responded to changes in climate and sea level, and how it eventually came to an end. The shallow seas of the Mesozoic were the stage on which much of the drama of this era played out. They were places of abundance and danger, of constant change and remarkable stability. And they remind us that the ocean is not a single, unchanging entity, but a mosaic of environments, each with its own character, its own creatures, and its own story. The surface of the Mesozoic ocean was where most of the energy entered the system. Sunlight penetrated the water, driving photosynthesis in microscopic plants called phytoplankton. These tiny organisms, invisible to the naked eye but present in trillions upon trillions, formed the base of the entire food web. Everything that lived in the ocean, from the smallest fish to the largest mosasaur, ultimately depended on them, and in the warm, nutrient-rich waters of the Mesozoic they thrived. Phytoplankton in the Mesozoic were not so different from those today. There were diatoms, single-celled algae encased in silica shells. There were dinoflagellates, flagellated cells that could swim weakly and sometimes produced bioluminescence, and there were coccolithophores, tiny algae that built intricate calcium carbonate plates around themselves. When these organisms died, their shells sank to the bottom, accumulating over millions of years to form the thick chalk deposits that give the Cretaceous its name. The word Cretaceous itself comes from the Latin for chalk, a testament to the sheer abundance of these tiny organisms. But phytoplankton were not the only primary producers. In shallow waters, seagrasses and algae carpeted the seafloor, providing food and habitat for a variety of creatures. Coral reefs, though less common than they would be in later eras, still existed, particularly in the Triassic and Jurassic. And by the Cretaceous, Rudist clams had taken over much of the reef-building role, creating massive structures that provided shelter and feeding grounds for countless other species. The surface waters were also where the first links in the food chain were forged. Zooplankton, tiny animals ranging from larval fish to copepods to jellyfish, fed on the phytoplankton. These in turn were eaten by small fish, which were eaten by larger fish, which were eaten by the marine reptiles and sharks at the top of the food web. It was a cascade of energy, each level supporting the next, all driven by the sun. The warm temperatures of the Mesozoic meant that this food web was incredibly productive. In today's oceans, the coldest waters are often the most productive because they hold more dissolved oxygen and because upwelling brings nutrients from the deep. But in the Mesozoic, with warm water everywhere, productivity was driven instead by the constant input of nutrients from the land. Rivers carried minerals and organic matter into the sea. Volcanic eruptions released iron and other micronutrients, and the shallow seas, with their constant mixing and exposure to sunlight, turned these nutrients into biomass with remarkable efficiency. The open ocean of the Mesozoic was not a featureless expanse. There were currents, driven by winds and by differences in temperature and salinity. These currents carried nutrients and organisms across vast distances, connecting different parts of the ocean and spreading life far and wide. The Tethys Sea, that great east-west seaway that stretched across the equatorial belt, acted as a highway for marine life. Creatures could migrate along it, spreading from the Pacific to the Atlantic or vice versa. And this connectivity meant that species could thrive over enormous ranges, adapting to different conditions but remaining connected to a larger population. There were also gyres, large circular currents similar to those we see today. These gyres concentrated floating debris, including mats of seaweed and logs washed out from rivers, creating floating islands of habitat. Small fish and invertebrates lived on these mats, feeding on the algae and detritus. Larger predators patrolled beneath them, waiting for prey to venture too far from safety. It was an ecosystem within an ecosystem, temporary but rich with life. The surface waters were also where the most dramatic interactions between marine reptiles took place. Mosasaurs hunted near the surface. Their eyes adapted to see in bright light, their bodies streamlined for speed. Plesiosaurs cruised through the water, their long necks scanning for fish or their short, powerful jaws snapping up ammonites. Sea turtles surfaced to breathe, their shells providing protection from predators but also making them slower and more visible. And then there were the pterosaurs, the flying reptiles that were not marine animals themselves but depended on the ocean for food. These creatures, with wingspans ranging from less than a metre to more than 10 metres, soared over the waves, dipping down to snatch fish from just below the surface. They were the seabirds of their time, filling the same ecological niche, and they were just as diverse and just as successful. Some species had teeth for gripping slippery prey, others had throat pouches like pelicans, and some had filter-feeding structures, straining tiny organisms from the water like modern flamingos. The surface of the Mesozoic ocean was a place of constant motion and constant danger. Predators were everywhere, from the surface to the depths. Prey had to be fast, camouflaged, or well defended, and the line between success and extinction was thin. A shift in current could bring nutrients and trigger a bloom supporting huge populations, or it could bring warm, oxygen-poor water, suffocating everything in its path. The surface was the interface between the ocean and the atmosphere, between the living world and the forces that shaped it, and it was where the drama of the Mesozoic seas played out in its most visible form. Yet for all its productivity and diversity, the surface was only a thin layer. Beneath it, the ocean extended downward for thousands of meters, and as you descended, the light faded, the temperature dropped, at least slightly, and the pressure increased. The surface was the beginning of the ocean, but the deep was its heart. Among all the creatures that lived in the Mesozoic ocean, none are more iconic than the great marine reptiles. These were the apex predators, the creatures that filled the same ecological roles as sharks, orcas, and sperm whales do today. But they were not fish. They were reptiles, air-breathing descendants of land-dwelling ancestors that had returned to the sea and adapted to a fully aquatic lifestyle. And they dominated the oceans for more than 150 million years, longer than mammals have dominated the land. The story of marine reptiles begins in the Triassic, shortly after the Great Permian extinction. The earliest forms were small, semi-aquatic creatures that likely spent part of their time on land. But they possessed certain advantages. They could swim, they could hold their breath for extended periods, and they had powerful jaws. Over time, natural selection favoured individuals that spent more time in the water, and eventually, some lineages made the transition complete. They lost their ability to walk on land, their limbs transformed into paddles, and their bodies became streamlined for swimming. They became, in every sense, creatures of the sea. The ichthyosaurs were among the first and most successful of these lineages. Their name means fish lizards, and the name is apt. They looked remarkably like modern dolphins with streamlined bodies, dorsal fins, and tail flukes. But they were reptiles, not mammals, and their ancestry was entirely different. Ichthyosaurs appeared in the early Triassic and quickly diversified. By the Jurassic, they ranged in size from less than a metre to more than 20 metres long. They had enormous eyes, the largest of any vertebrate ever, adapted for hunting in low light or at depth, and their teeth were sharp and conical, perfect for gripping fish and squid. Ichthyosaurs were fast swimmers. Their tails, shaped like a crescent moon, provided powerful propulsion. Their bodies, smooth and torpedo-shaped, moved through the water with minimal drag. They hunted by sight, using their huge eyes to spot prey from a distance, then accelerating in a burst of speed to catch it. They gave birth to live young, fully formed and ready to swim, a remarkable adaptation that freed them from the need to return to land. Fossils have been found of female ichthyosaurs preserved in the act of giving birth, their babies still inside or just emerging, frozen in time. Plesiosaurs were another major group, and they were very different from ichthyosaurs. Instead of a streamlined, fish-like body, plesiosaurs had broad, flat bodies with 4 large flippers. These flippers moved in a coordinated rowing motion, propelling the animal through the water with surprising efficiency. Some plesiosaurs had extraordinarily long necks, sometimes containing more than 70 vertebrae, with small heads at the end. These long-necked forms, like Elasmosaurus, are the creatures most people think of when they hear the word plesiosaur. But there were also short-necked forms, the plesiosaurs, with massive heads and powerful jaws. These were the true giants, some species reaching lengths of 15 meters or more, The long-necked plesiosaurs were likely ambush predators. They would swim slowly through the water, their necks held forward, scanning for fish. When prey came within range, the neck would strike, moving faster than the prey could react, the jaws snapping shut. It was a hunting strategy that required patience and precision, but it was effective. The short-necked plesiosaurs, by contrast, were pursuit predators. They hunted larger prey, including other marine reptiles, using their size and power to overwhelm their victims. Their jaws could generate enormous bite forces, and their teeth, thick and blade-like, could pierce through bone. But by the late Cretaceous, both the ichthyosaurs and the pliosaurs had declined. The ichthyosaurs disappeared entirely by about 90 million years ago, victims of environmental changes and perhaps competition from other predators. The pliosaurs held on a bit longer, but were also in decline. Into the void left by their disappearance came a new group, the mosasaurs. Mosasaurs were the last and perhaps the most successful of the great marine reptiles. They appeared in the Middle Cretaceous, around 98 million years ago, and within a few million years had spread across the world's oceans. They were related to modern monitor lizards and snakes, and their bodies reflected this ancestry. They were long and flexible, with powerful tails that moved side to side to propel them through the water. Their limbs had transformed into flippers, but unlike the paddles of plesiosaurs, mosasaur flippers were more like fins, used for steering rather than propulsion. Mosasaurs ranged in size from small species less than 3 meters long to giants like Mosasaurus hoffmanni, which could exceed 15 meters. They had long, toothy jaws, some species with teeth adapted for crushing shells, others with teeth for gripping slippery prey. They were fast, agile, and adaptable, hunting fish, ammonites, turtles, and even other mosasaurs. And unlike earlier marine reptiles, mosasaurs had a unique advantage. They could regulate their body temperature. Studies of their teeth have shown that they were warm-blooded, or at least partially so, which would have given them greater stamina and speed than their cold-blooded prey. Mosasaurs dominated the late Cretaceous seas in a way that no other marine reptile had before. They were found everywhere, from the western interior Seaway to the open Pacific, from the Tethys Sea to the coastal waters of Antarctica. They were the apex predators of their time, and they had no rivals. But their reign would not last. 66 million years ago, an asteroid struck the Earth, triggering a mass extinction that would wipe them out, along with the Ammonites, the Rudist clams, and countless other species. The age of marine reptiles came to an end. But while they lasted, the marine reptiles were the rulers of the Mesozoic seas. They filled every niche, from the smallest coastal hunter to the largest deep-water predator. They evolved in remarkable ways, adapting to life in the water with innovations that rival anything seen in the mammals that would later return to the sea. And their fossils, found in rocks around the world, remind us of a time when the ocean was a very different place, when reptiles, not mammals, were the kings of the deep. Below the sunlit surface of the Mesozoic ocean, where light began to fade but had not yet disappeared entirely, lay a region of transition. This was not the deep sea proper, not the cold, dark abyss that stretches for thousands of meters, but it was not the surface either. It was the twilight zone, the middle depths, where conditions shifted and creatures adapted to a world that was neither one thing nor the other. In modern oceans, this region is called the mesopelagic zone. It begins where the sunlight becomes too dim to support photosynthesis, usually around 200 meters, and extends down to about 1,000 meters. Here, the temperature drops sharply as you pass through the thermocline. The pressure increases, and the light, what little remains, is a deep, dark blue, fading into blackness. It is a world of constant migration, as creatures rise at night to feed in the rich surface waters and descend during the day to avoid predators. In the Mesozoic, this zone existed, but it was different. The thermocline was weaker and less stable. The water was warmer at depth than it is today, and the light, because the water was clearer and less productive in some areas, may have penetrated slightly deeper. But the fundamental challenge remained: how to survive in a place where food was scarce, where light was dim, and where predators lurked in the shadows. We know less about the middle depths of the Mesozoic ocean than we do about the surface or even the deep sea. This is because creatures that lived here are less likely to be preserved as fossils. Surface-dwelling organisms and those that lived on the seafloor are found in abundance in sedimentary rocks. But animals that lived in the water column in the open ocean away from the bottom are rarely preserved. Their soft bodies decay, their bones scatter, and the rocks that might contain them are often buried deep beneath younger sediments. But we do have clues. Ammonites, for instance, are found at many depths, and some species appear to have lived primarily in the Twilight zone. Their shells, with their gas-filled chambers, would have allowed them to hover at a particular depth, maintaining neutral buoyancy without expending energy. They could have fed on small prey, perhaps other plankton or detritus, using their tentacles to capture food, and they would have been prey themselves for the marine reptiles and fish that hunted in these depths. Fish were certainly present in the middle depths. Ancient lineages of bony fish and sharks, many of which have no living descendants, swam through these waters. Some had large eyes, adapted for seeing in low light. Others had bioluminescent organs, producing their own light to attract prey or communicate with others of their species. These adaptations, common in the Twilight Zone today, likely existed in the Mesozoic as well. There were also cephalopods other than ammonites. Belemnites, squid-like creatures with internal shells shaped like bullets, were common throughout the Mesozoic. They were fast swimmers, using jet propulsion to dart through the water. Their large eyes and streamlined bodies made them effective predators of small fish and crustaceans, and their fossils, particularly their bullet-shaped shells, are found in marine rocks around the world, evidence of their abundance and success. The middle depths were also a place of passage for marine reptiles. Plesiosaurs, with their long necks and paddles, could have dived to considerable depths in search of prey. Mosasaurs, with their flexible bodies and powerful tails, were capable swimmers that could move between the surface and the depths with ease, and some species may have spent much of their time in the Twilight Zone hunting the abundant ammonites and fish that lived there. But the middle depths were not just a hunting ground, they were also a refuge. During Oceanic Anoxic events, when the surface waters became oxygen depleted and hostile, some creatures may have retreated to deeper, better oxygenated waters. The thermocline, weak as it was, could still act as a barrier, preventing oxygen-poor surface water from mixing with the deeper layers. And creatures that could tolerate lower oxygen levels, or that could migrate vertically to find oxygenated zones, would have had an advantage. The middle depths were also where much of the ocean's nutrient cycling occurred. Organic matter sinking from the surface, dead plankton, feces, molted shells, would pass through the Twilight Zone on its way to the bottom. As it sank, it was consumed by bacteria and other decomposers, releasing nutrients back into the water. These nutrients could then be carried by currents back to the surface, where they would fuel new blooms of plankton. This recycling process, known as the biological pump, is essential to the functioning of the ocean, and it was just as important in the Mesozoic as it is today. But the middle depths were also a place of danger. The low light made it hard to see predators approaching. The pressure, while not as extreme as in the abyss, was still significant, and the scarcity of food meant that competition was fierce. Creatures that lived here had to be efficient, adaptable, and resilient. They had to make the most of every opportunity, whether that meant scavenging a piece of falling detritus or launching a quick ambush on an unwary fish. The middle depths of the Mesozoic Ocean remain one of the least understood parts of this ancient world. We know they existed, we know they were inhabited, but the details, the specific creatures that lived there, their behaviours, their interactions, remain largely a mystery. Perhaps future discoveries will shed more light on this twilight realm. Perhaps new fossils preserved in unexpected places will reveal the secrets of the creatures that swam in the dim waters between surface and abyss. Until then, the middle depths remain a place of shadow and speculation, a reminder of how much we still have to learn about the oceans of the past. If there is one group of animals that epitomizes the Mesozoic seas, it is the Ammonites. These spiral-shelled cephalopods were everywhere, from the shallowest coastal waters to the depths of the open ocean. They came in an astonishing variety of forms, from tiny coils no bigger than a fingernail to giants measuring 2 meters across. They were so abundant and so diverse that they are used as index fossils, markers that allow geologists to date rocks and correlate layers across vast distances. And they dominated the Mesozoic seas for more than 130 million years, only to vanish in the extinction event that ended the era. Ammonites were related to modern squids, octopuses, and nautiluses, but they were unique in having external chambered shells. The shell was coiled in a flat spiral, though some species evolved bizarre uncoiled forms. Inside the shell were a series of chambers, separated by thin walls called septa. Only the outermost chamber, the body chamber, was occupied by the living animal. The inner chambers were filled with gas or liquid, which the ammonite could regulate to control its buoyancy. This allowed it to hover at a particular depth, ascending or descending as needed without expending energy. The shell itself was a masterpiece of engineering. It was made of aragonite, a form of calcium carbonate, arranged in thin layers that provided strength without excessive weight. The septa, the walls separating the chambers, were not flat but folded into intricate patterns. These patterns, visible on the outside of the shell where the septa met the wall, are called sutures. In early ammonoids from the Paleozoic, the sutures were simple, but by the Mesozoic they had become extraordinarily complex with lobes and saddles that twisted and turned in fractal-like patterns. The purpose of these complex sutures is still debated, but they likely helped to strengthen the shell, allowing ammonites to dive deeper without being crushed by the pressure. Ammonites ranged in size from tiny species no bigger than a coin to giants like Parapuzosia, which could reach diameters of more than 2 meters. The larger specimens weighed hundreds of kilograms. Their shells were often ornamented with ribs, nodes, spines, or other structures that may have served various purposes, streamlining for faster swimming, defense against predators, or simply structural support. The soft body of an ammonite, which is rarely preserved, likely resembled that of a nautilus. There would have been a head with a beak and large eyes, surrounded by tentacles for capturing prey. The tentacles were probably lined with suckers or hooks, allowing the ammonite to grip slippery fish or crustaceans. The animal would have moved by jet propulsion, drawing water into its body cavity and expelling it forcefully through a funnel, pushing itself backward through the water. Ammonites occupied a wide range of ecological niches. Some were fast swimmers, hunting active prey in the open ocean. Others were slower, drifting in the water column and feeding on plankton or detritus. Some species lived near the surface, others in the twilight zone, and a few may have ventured into the deeper waters. This diversity of lifestyles is reflected in the diversity of shell shapes and sizes. Small, streamlined shells indicate fast-swimming predators. Large, heavily ornamented shells suggest slower, more heavily armoured forms. Uncoiled, heteromorph shells are thought to have belonged to species with specialised feeding strategies, or those that lived in particular environments. The abundance of ammonites in Mesozoic seas is hard to overstate. In some rock formations, particularly those formed in shallow seas, ammonite fossils are so common that they form entire layers, packed so tightly that they overlap. These mass accumulations, sometimes called ammonite pavements, are evidence of enormous populations and favourable conditions. When conditions shifted, perhaps due to changes in temperature, oxygen levels or food availability, entire populations could be wiped out, leaving behind beds of shells that would eventually fossilise. Ammonites were also important players in the Mesozoic food web. They were prey for a wide variety of predators. Mosasaurs, with their powerful jaws and sharp teeth, crushed ammonite shells to get at the soft flesh inside. Fossils of ammonite shells have been found with mosasaur tooth marks, puncture wounds, and crushed chambers, evidence of these violent encounters. Plesiosaurs, fish, and even other cephalopods likely fed on ammonites as well. At the same time, ammonites themselves were predators, feeding on smaller animals and helping to regulate the populations of their prey. But despite their success, ammonites were not immune to extinction. Several times during the Mesozoic, particularly during Oceanic Anoxic events, ammonite diversity crashed. Entire families disappeared, leaving only a few surviving lineages to rebuild. These survivors radiated, diversifying into new forms and filling the empty niches. This pattern of extinction and recovery happened multiple times, shaping the evolution of the group over tens of millions of years. The final extinction, at the end of the Cretaceous, was total. Not a single ammonite species survived the asteroid impact and its aftermath. The reasons are still debated. Some scientists believe that the collapse of the food web, particularly the die-off of plankton that formed the base of the marine ecosystem, starved the ammonites. Others point to the environmental changes that followed the impact: falling temperatures, acidic oceans, and the disruption of ocean currents. Whatever the cause, the result was the same: After more than 130 million years of dominance, the Ammonites vanished. Today, their closest living relative is the nautilus, a creature that has changed little in hundreds of millions of years. Nautiluses still swim in the deep waters of the Pacific and Indian Oceans, their shells coiled in the same spiral pattern as their ancient cousins. But they are a shadow of what the Ammonites once were, a reminder of a time when cephalopods ruled the seas in a way they never would again. While the Mesozoic seas are often associated with ammonites and marine reptiles, there was another group of creatures that played a crucial, if less celebrated, role in shaping the ocean ecosystems of this time. These were the Rudist clams, bizarre bivalves that built massive reef structures across the tropical seas of the Cretaceous. They were so successful that for a time they replaced corals as the dominant reef builders, creating habitats that supported countless other species. And like so many other creatures of the Mesozoic, they vanished in the extinction event that ended the era. Rudist clams first appeared in the late Jurassic, around 150 million years ago, but it was during the Cretaceous that they truly came into their own. They were members of the bivalve family, related to modern clams and mussels, but they looked nothing like their living relatives. Instead of having two symmetrical shells, Rudists had wildly asymmetrical forms. One shell, usually the lower one, was large, thick and conical or coiled, and it was cemented to the seafloor. The other shell, the upper one, was much smaller and sat on top like a lid or cap. The animal lived inside, filter feeding on plankton and detritus. The shapes of Rudist shells were extraordinarily diverse. Some species had straight, cone-shaped shells that stood upright like ice cream, cones. Others had shells that coiled in spirals, resembling miniature snail shells. Still others had shells that twisted and curved in irregular shapes. This diversity of form is one of the reasons Rudist was so successful. Different shapes were adapted to different environments and different feeding strategies, allowing Rudist to colonize a wide range of habitats. Rudist clams were gregarious, meaning they lived in dense clusters. Individual Rudists would attach to each other, building up over time to form massive reef structures. These reefs could extend for hundreds of meters, rising several meters above the seafloor. They provided shelter for fish, crustaceans and other invertebrates, creating complex ecosystems that rivaled those of modern coral reefs. And because Rudists were filter feeders, they played a crucial role in clearing the water of plankton and detritus, improving water quality and maintaining the health of the ecosystem. The reefs built by Rudists were particularly common in the Tethys Sea, the warm tropical seaway that stretched across the equatorial belt during the Cretaceous. The combination of warm water, high sea levels and abundant nutrients made this an ideal environment for Rudists. They thrived in the shallow seas, building reefs along the margins of continents and on submerged platforms. Fossils of Rudist reefs are found today in places as far apart as Mexico, the Mediterranean, the Middle East and Southeast Asia, evidence of their widespread distribution. But Rudists were not the only reef builders during the Mesozoic. Corals, which had been devastated by the Permian extinction, gradually recovered during the Triassic and Jurassic. By the Cretaceous, scleractinian corals, the ancestors of modern reef-building corals, were common in many areas. But they did not dominate. Rudists outcompeted them in many environments, particularly in the warmest, most productive seas. This shift in dominance from corals to Rudists and then back to corals after the extinction is one of the most intriguing aspects of Mesozoic reef ecology. Why did Rudists become so successful? There are several possible explanations. One is that they were better adapted to the warm, low-oxygen conditions that sometimes occurred in Cretaceous seas. Corals are sensitive to low oxygen levels and to changes in water chemistry, but Rudists may have been more tolerant. Another possibility is that Rudists grew faster than corals, allowing them to outcompete for space on the seafloor. Still another is that the high productivity of Cretaceous seas, driven by volcanic eruptions and nutrient input from the land, favoured filter feeders like Rudists over photosynthetic organisms like corals. Whatever the reason, Rudist reefs were a defining feature of the Cretaceous ocean. They shaped the physical environment, providing structure and habitat. They influenced the chemistry of the water, filtering out plankton and releasing calcium carbonate as they built their shells, and they supported a rich diversity of life, from tiny invertebrates living between the shells to large predators hunting in the waters above. But like so many other Mesozoic creatures, Rudists were vulnerable to environmental change. Throughout the Cretaceous, there were several extinction events that hit Rudist populations hard. These events, often associated with Oceanic Anoxic events or changes in sea level, caused declines in Rudist diversity and the collapse of reef ecosystems. But each time, Rudists recovered, rebuilding their reefs and diversifying once more. The final blow came at the end of the Cretaceous. The asteroid impact and its aftermath destroyed the shallow seas where Rudists thrived. Falling sea levels drained the Epicontinental seaways. Changes in ocean chemistry, particularly acidification caused by sulfur dioxide released by the impact, made it difficult for Rudists to build their shells, and the collapse of the food web as plankton die-offs cascaded through the ecosystem starved the filter-feeding Rudists. Within a few thousand years they were gone. Today no descendants of the Rudist clams remain. They left no survivors, no lineages that adapted and carried on. But their legacy is preserved in the rocks, in the limestone formations that were once their reefs, and in the fossils that tell us what they looked like and how they lived. And they remind us that the ocean ecosystems of the past were not just different in the species they contained, but in the very structure and function of those ecosystems. To understand the Mesozoic ocean, we need to look beyond the creatures that lived there and examine the physical and chemical properties of the water itself. The ocean is not just a habitat, it is a dynamic system, constantly moving, constantly changing, shaped by forces both internal and external. And in the Mesozoic, these forces created an ocean that was fundamentally different from the one we know today. One of the most important aspects of ocean chemistry is the distribution of dissolved oxygen. Oxygen is essential for most marine life. Fish, reptiles, and invertebrates all need it to survive. Today, oxygen enters the ocean primarily at the surface, where the water is in contact with the atmosphere and where photosynthesis by plankton produces oxygen as a byproduct. From there, it is mixed downward by currents and by the formation of cold, dense water at the poles, which sinks and carries oxygen with it into the deep. But in the Mesozoic, this system worked differently. The lack of polar ice caps meant that cold, dense water formation was much weaker. The water that did sink was warmer and less dense than today's deep water, so it carried less oxygen. And because warm water holds less dissolved oxygen than cold water, the entire ocean had lower oxygen levels to begin with. This created a situation where large parts of the ocean, particularly at depth and in areas with weak circulation, were oxygen poor or even anoxic. These low oxygen zones, called oxygen minimum zones, are found in today's oceans as well, but they are much more limited in extent. In the Mesozoic, they were larger and more widespread. They occurred in the middle depths, typically between a few hundred and a few thousand meters down, where oxygen was consumed by decaying organic matter faster than it could be replenished. They also occurred in the deep basins of epicontinental seas, where circulation was restricted and where the water could become stagnant. The consequences of these oxygen minimum zones were profound. They limited where marine life could survive. Creatures that needed oxygen, which was most of them, had to avoid these zones or pass through them quickly. But some organisms adapted to low oxygen conditions. Certain species of fish, crustaceans, and even ammonites developed physiological adaptations that allowed them to tolerate hypoxic environments. They had more efficient gills, slower metabolisms, or the ability to store oxygen in their tissues. But there were limits to adaptation. When oxygen levels dropped too low, even the most tolerant species could not survive. These extreme events, called Oceanic Anoxic events or OAEs, occurred several times during the Mesozoic. They were times when large expanses of the ocean, sometimes encompassing entire basins, lost most or all of their dissolved oxygen. The water turned toxic, not just oxygen poor but actively harmful, often containing hydrogen sulfide, a poison that killed anything that encountered it. The causes of oceanic anoxic events are complex and still debated, but most scientists agree that they were triggered by a combination of factors. Volcanic eruptions released carbon dioxide and other gases into the atmosphere, driving global warming. Warmer temperatures increased weathering on land, washing nutrients into the sea. These nutrients fueled massive blooms of plankton, which died and sank, consuming oxygen as they decayed. At the same time, warmer water and weaker circulation meant that oxygen was not being replenished. The result was a feedback loop. More nutrients led to more plankton, which led to more decay, which consumed more oxygen, which made the problem worse. During these events, the ocean became stratified, with a layer of oxygen-poor or anoxic water sitting below a thin layer of oxygenated surface water. Creatures that could not tolerate these conditions died in massive numbers. The seafloor became covered in the remains of dead organisms, which could not decay in the oxygen-free environment. Over time, these organic-rich sediments were buried and compressed, forming the black shales that we see today in rocks of Mesozoic age. But oceanic anoxic events were not permanent. They lasted for tens of thousands to hundreds of thousands of years, and then they ended. The triggers, whether volcanic eruptions or changes in circulation, eventually stopped, oxygen levels slowly recovered, and life returned, recolonizing the areas that had been dead zones. But each event left its mark, both in the rock record and in the evolution of marine life. Species that could not tolerate low oxygen went extinct. Those that survived were often those that could adapt to changing conditions, and they became the ancestors of the next generation. Ocean circulation in the Mesozoic was also different. Today, the global ocean is driven by a system called thermohaline circulation, where cold, dense water formed at the poles sinks and drives a slow conveyor belt of deep currents. But in the Mesozoic, with no polar ice and warmer temperatures everywhere, this system was much weaker. Instead, circulation was driven more by winds and by differences in salinity. Evaporation in the tropics made surface water saltier and denser, causing it to sink. This created a different pattern of currents, one that was less efficient at mixing the ocean and transporting oxygen. Salinity itself was also variable. In the open ocean, salinity was probably similar to today's, around 35 parts per thousand. But in restricted basins, especially in the Tethys Sea during times of high evaporation, salinity could become much higher. These hypersaline conditions created dense brines that sank to the bottom, forming stratified layers and contributing to anoxia. Conversely, in areas where rivers discharged large amounts of fresh water, such as the mouths of the great rivers draining into the western interior Seaway, salinity could drop, creating brackish conditions that favoured different communities of organisms. The chemistry of the Mesozoic ocean was also affected by the buildup of carbon dioxide in the atmosphere. Higher CO2 levels meant that more of it dissolved into the ocean, forming carbonic acid and making the water more acidic. This process, called ocean acidification, affected organisms that built shells or skeletons out of calcium carbonate, including ammonites, rudists, and plankton. In extreme cases, acidification could dissolve these structures, making it difficult or impossible for these organisms to survive. Yet despite all these challenges, life found a way. The Mesozoic ocean was a place of extremes of warmth and anoxia, of abundance and extinction. But it was also a place of adaptation and resilience. And the creatures that lived there, from the smallest plankton to the largest marine reptiles, were shaped by the chemistry and circulation of the water in which they swam. Among the most dramatic and catastrophic events in the Mesozoic ocean were the Oceanic Anoxic events. These were times when large areas of the sea lost most or all of their dissolved oxygen, turning into dead zones where almost nothing could live. They occurred multiple times during the Mesozoic, each lasting for tens of thousands to hundreds of thousands of years, and each leaving behind layers of black organic-rich shale as evidence of their occurrence. These events were not just local phenomena, but global catastrophes that reshaped marine ecosystems and left lasting marks on the evolution of life. The first major oceanic anoxic event of the Mesozoic occurred in the early Jurassic, around 183 million years ago. Known as the torsion OAE, this event coincided with massive volcanic eruptions in what is now South Africa. The eruptions released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, triggering global warming and acidifying the ocean. Sea temperatures rose by perhaps 5 to 10 degrees Celsius, and as the oceans warmed, they lost oxygen. The effects were devastating. In many parts of the world, the seafloor became anoxic. Organisms that lived there, including many species of bivalves, brachiopods, and benthic foraminifera, died in massive numbers. Ammonites, which had been abundant and diverse, suffered a major extinction, with many families disappearing. The survivors were those that could tolerate low oxygen, or that could migrate to better oxygenated waters. But even they were affected, with reduced populations and limited ranges. The black shales deposited during the torsion OAE are found around the world, from Europe to South America to the Arctic. These shales, rich in organic matter, are evidence of the anoxic conditions. They contain fossils of organisms that died and sank to the bottom, where they were preserved in the oxygen-free sediments. Some of these fossils are exquisitely preserved, with soft tissues and even internal organs visible, a testament to the lack of decay in the anoxic environment. The Cretaceous saw several more oceanic anoxic events, each associated with volcanic activity and each leaving its mark on the rock record. The most famous is probably Oceanic Anoxic Event 2, or OAE2, which occurred around 93 million years ago during the Cenomanian-Turonian boundary. This event coincided with the eruption of the Kerguelen Plateau in the southern Indian Ocean, one of the largest volcanic events in Earth's history. The eruptions released vast amounts of CO2, driving global temperatures even higher. Sea surface temperatures in the tropics may have reached 35 to 40 degrees Celsius, hot enough to threaten the survival of many organisms. OAE2 had profound effects on the ocean. Anoxic zones expanded, covering large parts of the Atlantic and Tethys oceans. The seafloor became a graveyard, littered with the remains of organisms that could not survive. Planktonic foraminifera, tiny protozoans that floated in the water column, suffered a major extinction, with many species disappearing. Ammonites, already declining from earlier events, were hit hard again, and even the marine reptiles, which had been thriving, saw declines in some groups. But OAE2 also had some unexpected effects. The massive amounts of organic matter that accumulated on the seafloor during this time eventually became the source rocks for much of the world's oil. The anoxic conditions prevented decay, allowing the organic matter to be buried and compressed over millions of years. Today, when we drill for oil, we're often tapping into deposits that formed during oceanic anoxic events, a strange legacy of these ancient catastrophes. The causes of oceanic anoxic events are complex and involve multiple feedback loops. Volcanic eruptions release CO2, which warms the planet. Warmer temperatures increase weathering on land, washing nutrients into the ocean. Nutrients fuel plankton blooms, which produce organic matter. The organic matter sinks and decays, consuming oxygen. Warmer water holds less oxygen to begin with and circulates more slowly, so oxygen is not replenished. The result is anoxia, which can persist for thousands of years. But there is also evidence that oceanic anoxic events were not entirely uniform. They varied in intensity and extent. Some were truly global, affecting all the world's oceans. Others were more regional, confined to particular basins or areas with restricted circulation. And within each event there were likely fluctuations, times when oxygen levels improved temporarily before declining again. This variability made them even more difficult for organisms to survive. Adaptation to low oxygen could be a successful strategy, but if conditions improved and then worsened again, even adapted species could be overwhelmed. The recovery from oceanic anoxic events was slow. It took tens of thousands to hundreds of thousands of years for oxygen levels to return to normal. During this time, the ocean was in a state of transition. Anoxic zones gradually shrank as circulation improved and as the organic matter that had been consuming oxygen was finally buried and removed from the system. Pioneer species, those that could tolerate marginal conditions, began to recolonize the dead zones. And slowly, over time, the full diversity of marine life returned, but the scars remained. Each oceanic anoxic event left behind layers of black shale, markers in the rock record that geologists use to date and correlate rocks around the world. And each event reshaped the evolution of marine life, eliminating species that could not adapt and favoring those that could. In this way, oceanic anoxic events were not just catastrophes, but also engines of evolution, driving change and creating opportunities for new lineages to emerge. Below the shallow seas and the twilight zone, below the oxygen minimum zones and the layers of warm circulating water, lay the true deep sea. This was the abyss, the cold, dark realm that covers more than half the planet's surface today, and that covered even more of it during the Mesozoic. It was a place of immense pressure, of near total darkness, and of conditions so extreme that life there had to follow entirely different rules. Today's deep sea, defined as depths below 1,000 meters, is a cold, stable environment. Temperatures hover just above freezing, typically between 0 and 4 degrees Celsius. The pressure is crushing, increasing by 1 atmosphere for every 10 meters of depth. At the deepest points, in the Hadal zone of ocean trenches, the pressure exceeds 1,000 atmospheres, enough to compress even steel. And there is no sunlight. None at all. The only light comes from bioluminescent organisms, creatures that produce their own glow through chemical reactions. But in the Mesozoic, the deep sea was warmer. Deep ocean temperatures during the Cretaceous were perhaps 15 to 20 degrees Celsius, far warmer than today. This warmth had profound effects on the chemistry and biology of the deep. Warmer water holds less oxygen, so the deep sea was more oxygen-poor than it is now. Warmer water also affects the solubility of calcium carbonate, making it easier for shells and skeletons to dissolve. And warmer temperatures affect metabolic rates, potentially allowing deep-sea organisms to be more active than their modern counterparts. The source of this warmth is still debated. Today, the deep ocean is cold because cold water forms at the poles and sinks, carrying its chill with it. But in the Mesozoic, with no polar ice and warmer temperatures everywhere, this process was weaker. The water that did sink was warmer to begin with, and there may have been other sources of heat as well. Volcanic activity, particularly at mid-ocean ridges where a new seafloor is created, releases heat into the deep ocean. During the Mesozoic, when seafloor spreading was more rapid, this heat flux may have been greater. What lived in the deep sea of the Mesozoic? This is one of the great mysteries of paleontology. Deep-sea organisms are rarely preserved as fossils because the deep-sea floor is constantly being subducted at tectonic plate boundaries, carrying the sediments and fossils with it. The oldest preserved deep-sea sediments are only about 180 million years old from the Jurassic, and even these are rare. Most of what we know about the Mesozoic deep sea comes from indirect evidence, chemical signatures in rocks, the distribution of certain types of sediments, and comparisons with modern deep-sea ecosystems. We know there were fish in the deep. Fossils of deep-sea fish from the Cretaceous have been found, though they are rare. These fish had large eyes, adapted for seeing in low light, and specialized jaws for capturing prey. They were likely similar to modern deep-sea fish in form and function, though the species themselves were entirely different. There were also crustaceans, mollusks, and other invertebrates, creatures that scavenged on the constant rain of organic matter falling from above. Ammonites too may have ventured into the deep. Some species have been found in sediments deposited in deep water, suggesting they lived at considerable depths. Their shells, with their gas-filled chambers, would have allowed them to maintain buoyancy even under high pressure, though there were limits. Too deep and the pressure would crush the chambers, causing the shell to implode. But within their limits, ammonites could have occupied the upper reaches of the deep sea, hunting or scavenging in the twilight between the mesopelagic and the abyssal zones. The seafloor itself was a different world. In areas with good oxygen supply, the bottom was covered in fine sediments, oozes made of the remains of plankton that had died and sunk. These sediments were home to burrowing organisms, worms, mollusks, and crustaceans that fed on the organic matter. But in areas with poor oxygen, the seafloor was lifeless, covered in black mud where nothing could survive. These anoxic basins, common during oceanic anoxic events, preserved organic matter in extraordinary detail, creating the black shales that are so valuable for understanding ancient ocean conditions. There may also have been deep-sea vents, hydrothermal systems, where superheated water, rich in minerals, spewed from cracks in the seafloor. These vents, powered by volcanic activity, are oases of life in the modern deep sea, supporting ecosystems that do not depend on sunlight, but on chemosynthesis, the use of chemical energy from the vent fluids. Did such ecosystems exist in the Mesozoic? Almost certainly. The same volcanic processes that drive vents today were active then. But we have no direct evidence, no fossils from Mesozoic vent communities, because those environments are particularly hard to preserve. The deep sea of the Mesozoic was a frontier, a vast, unexplored realm that covered most of the planet. It was warmer than today's abyss, but still a place of darkness and pressure. It was home to creatures we can barely imagine, adapted to conditions that push the limits of life. And it remains one of the least understood aspects of the Mesozoic ocean, a reminder that even with all our knowledge, there is still so much we do not know about the past. The ocean of the Mesozoic did not exist in isolation. It was shaped by the movement of continents, the opening and closing of ocean basins, and the slow, inexorable forces of plate tectonics. At the beginning of the Mesozoic, the world's land masses were joined in the supercontinent Pangaea, surrounded by the vast Panthalassa Ocean. But by the end of the era, Pangaea had broken apart, creating the familiar pattern of continents and oceans that we know today. And this breakup had profound effects on the ocean, reshaping its circulation, its chemistry, and the life it contained. The breakup of Pangaea began in the Triassic and accelerated during the Jurassic and Cretaceous. The first rifts opened in the Tethys Sea, a narrow seaway that separated the northern and southern halves of Pangaea. As the rift widened, seawater flooded in, creating a shallow tropical ocean that stretched from west to east across the equatorial belt. The Tethys Sea became one of the most important marine environments of the Mesozoic, home to coral reefs, Rudist reefs, ammonites, and marine reptiles. It was a place of warmth and productivity, a highway for marine life that connected the Pacific and the nascent Atlantic. The opening of the Atlantic Ocean was a slower process. It began in the Jurassic, around 180 million years ago, when a rift opened between what is now North America and Africa. Magma welled up from the mantle, creating new seafloor and pushing the continents apart. At first, the Atlantic was narrow, more of a seaway than an ocean. But over millions of years it widened, becoming a true ocean basin. By the end of the Cretaceous, it was thousands of kilometers wide, though still narrower than it is today. The opening of the Atlantic had profound effects on ocean circulation. It created a new pathway for currents, allowing water to flow between the northern and southern hemispheres. It also created new coastlines, new habitats for marine life, and it isolated populations of organisms, allowing them to evolve independently on either side of the growing ocean. Species that had once been widespread across Pangaea now diverged, becoming distinct lineages in the Atlantic and Pacific. The Indian Ocean, too, began to form during the Mesozoic. India, which had been part of the southern supercontinent Gondwana, rifted away from Africa and Antarctica during the Jurassic and began drifting northward. As it moved, it opened a new ocean basin behind it. This process continued through the Cretaceous, with India eventually colliding with Asia in the Cenozoic, creating the Himalayas. But during the Mesozoic, the Indian Ocean was a warm tropical sea, home to its own unique ecosystems. The Pacific Ocean, or Panthalassa, was by far the largest ocean during the Mesozoic, covering more than half the planet's surface. It was an ancient ocean, older than Pangaea itself, and it had existed for hundreds of millions of years. Unlike the Atlantic and Indian, which were young and growing, the Pacific was old and shrinking, its seafloor being subducted at its margins as the continents spread apart. This constant subduction meant that very little of the Mesozoic Pacific seafloor remains today. What we know about it comes mostly from volcanic islands, seamounts, and the sediments that were scraped off the subducting plate and accreted onto the continents. The breakup of continents also affected sea level. As new ocean basins opened, the mid-ocean ridges where new seafloor was created became larger and more active. These ridges are essentially underwater mountain ranges, and as they grew, they displaced seawater, pushing it up onto the continents. This, combined with the thermal expansion of warmer water, caused sea levels to rise dramatically during the Mesozoic. By the Cretaceous, sea level was 100 to 200 meters higher than today, flooding vast areas of the continents and creating the Epicontinental seas that were so important to Mesozoic marine life. The configuration of continents also affected climate. When Pangaea was intact, the interior of the supercontinent was hot and dry, far from any ocean. But as the continents broke apart, more land was exposed to the moderating influence of the sea. Coastal areas became wetter and cooler, and the opening of new seaways allowed ocean currents to redistribute heat more efficiently, evening out temperatures across the globe. This contributed to the warm, equable climate of the Mesozoic, where the difference between the equator and the poles was much less than it is today. But the breakup of continents was not without its challenges. The opening of new ocean basins was often accompanied by massive volcanic eruptions as magma welled up from the mantle. These eruptions released carbon dioxide and other gases into the atmosphere, driving global warming. They also released metals and nutrients into the ocean, which could trigger plankton blooms and contribute to oceanic anoxic events. And the rearrangement of continents affected ocean circulation in ways that could reduce oxygen levels and create dead zones. By the end of the Mesozoic, the world looked much more like the modern world. The Atlantic had opened, separating the Americas from Europe and Africa. India had broken free and was drifting northward. Australia and Antarctica were still joined but beginning to separate. And the Pacific, though still the largest ocean, was shrinking as the continents spread and new ocean basins grew. The stage was set for the Cenozoic, the age of mammals, and for the eventual configuration of continents and oceans that we know today. All eras come to an end, and for the Mesozoic that end came swiftly and catastrophically. 66 million years ago, an asteroid 10 kilometers across struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of atomic bombs. It vaporized the asteroid itself, along with the rock it struck, sending a cloud of dust, soot and debris high into the atmosphere. And it triggered a chain of events that would kill off 75% of all species on Earth, including all the non-avian dinosaurs, the marine reptiles, the ammonites and the Rudist clams. The effects on the ocean were immediate and devastating. The impact created a massive tsunami, a wall of water hundreds of meters high that swept across the Gulf of Mexico and into the Atlantic. Coastal areas were inundated, their ecosystems destroyed. The sediments deposited by this tsunami are found today in rocks all along the Gulf Coast, mixed with fragments of the asteroid itself, small spherules of glassy rock formed from molten droplets that rained back down from the sky. But the tsunami was just the beginning. The dust and soot thrown into the atmosphere blocked sunlight, creating what is known as an impact winter. Temperatures plummeted, photosynthesis stopped, and, without sunlight, the base of the ocean food web, the phytoplankton, died en masse. Their die-off cascaded through the ecosystem. The zooplankton that fed on them starved, the fish that fed on the zooplankton starved, and the marine reptiles and other predators at the top of the food web, with nothing left to eat, starved as well. The collapse of the phytoplankton also had another effect. When plankton photosynthesize, they produce oxygen. With photosynthesis shut down, oxygen levels in the surface ocean dropped, and as dead plankton sank and decayed, they consumed what oxygen remained, creating anoxic zones that spread across the ocean. The combination of cold, darkness, and lack of oxygen made the ocean nearly uninhabitable. At the same time, the impact released enormous quantities of sulfur dioxide and carbon dioxide into the atmosphere. The sulfur dioxide combined with water vapor to form sulfuric acid, which fell as acid rain, acidifying the ocean and making it difficult for organisms with calcium carbonate shells to survive. Ammonites with their delicate shells were particularly vulnerable. Planktonic foraminifera, Rudist clams and many other groups that depended on building shells were also hit hard. The ocean's chemistry had turned hostile. In the deep sea, the effects were less immediate but no less profound. The rain of organic matter from the surface, which had sustained deep-sea life for millions of years, slowed to a trickle. Deep-sea organisms, already living on the edge of survival, starved. The seafloor, once covered in fine sediments rich in the remains of plankton, became barren. And while some deep-sea creatures survived, many lineages went extinct, but not everything died. Some organisms, particularly those that could survive on detritus, or that had generalized diets, made it through. Small mammals, which could scavenge and burrow, survived. Crocodiles and turtles, which could go long periods without food, survived. Some fish, particularly those that lived in fresh water, or that could tolerate a wide range of conditions, survived. And some marine invertebrates, particularly those that lived on the seafloor and could filter feed on whatever organic matter remained, survived. The recovery took a long time. The dust and soot eventually settled out of the atmosphere and sunlight returned. Phytoplankton populations rebounded, though the species that dominated were different from those before. Ecosystems slowly rebuilt, but they were different too. The giant marine reptiles were gone, never to return. The ammonites were gone, leaving only the nautilus as a distant cousin. The Rudist clams were gone, and corals gradually reclaimed their role as reef builders. But the extinction also created opportunities. With the great predators gone, smaller creatures could expand and diversify. Teleost fish, which had been present but not dominant during the Mesozoic, radiated into an astonishing variety of forms. Marine mammals, which would not appear for another 10 million years, would eventually fill the niches left empty by the marine reptiles. And the ocean, though changed, continued to thrive. The end of the Mesozoic was the end of an era, but it was also a beginning. The ocean that emerged from the ashes of the asteroid impact was a different ocean, shaped by the catastrophe but still full of life, still evolving, still endlessly adapting to a changing world. The ocean of the Mesozoic is gone. The creatures that swam in it, from the tiny ammonites to the giant mosasaurs, are extinct. The warm, shallow seas that covered the continents have drained away, and the warm, sluggish deep sea has been replaced by the cold, dark abyss we know today. But the Mesozoic ocean has not disappeared entirely. It has left behind clues, traces, and echoes written in the rocks, in the chemistry of ancient shells, and in the shapes of the continents themselves. The most direct evidence of the Mesozoic ocean comes from fossils. Ammonite shells preserved in limestone and shale are found on every continent. Marine reptile skeletons lying in the rock as they fell to the seafloor millions of years ago tell us about the predators that ruled these seas. Rudist reefs, now turned to stone, form cliffs and outcrops in places far from any modern ocean. And the tiny shells of foraminifera and coccolithophores, invisible to the naked eye but present in trillions, make up entire layers of rock, the chalk and limestone that are quarried and used for building. But fossils are only part of the story. The sediments themselves, the layers of mud, sand, and shell that accumulated on the Mesozoic seafloor, contain a wealth of information. The colour of the rock tells us about oxygen levels. Black shales indicate anoxic conditions. Red beds indicate oxygenated environments. The grain size tells us about water energy. Fine mud indicates calm, deep water. Coarse sand indicates strong currents or shallow, wave-swept environments. And the chemistry of the rock, the isotopes locked in ancient minerals, tells us about temperature, salinity, and the composition of the atmosphere. These isotopes, particularly oxygen and carbon, are some of the most powerful tools we have for reconstructing ancient oceans. Oxygen isotopes in shells tell us about temperature. The ratio of oxygen 16 to oxygen 18 varies with temperature, and by measuring this ratio in fossil shells, we can estimate what the water temperature was when the shell formed. Carbon isotopes tell us about the carbon cycle, about photosynthesis and respiration, about the burial of organic matter and the release of carbon dioxide. By analysing carbon isotopes in rocks of different ages, we can track how the ocean's chemistry changed over time. Strontium isotopes tell us about weathering and erosion on land. Rivers carry dissolved strontium from the continents into the ocean, and the isotopic composition of that strontium varies depending on the type of rock being weathered. By measuring strontium isotopes in marine rocks, we can infer what was happening on land, whether continents were uplifting and eroding, whether volcanic activity was high or low. And then there are the sedimentary structures, the physical features preserved in the rock. Ripple marks tell us about currents. Burrows tell us about the organisms that lived on or in the seafloor. Layers of ash tell us about volcanic eruptions. Drop stones, large boulders embedded in fine sediment, tell us about ice rafting, though this is rare in the Mesozoic. Each feature is a clue, a piece of evidence that helps us reconstruct what the ancient ocean was like. The legacy of the Mesozoic ocean extends beyond the rocks. The oil and gas we extract from the ground today comes in large part from organic matter deposited in Mesozoic seas. The black shales formed during Oceanic and Anoxic events, rich in the remains of plankton and other organisms, are the source rocks for much of the world's petroleum. The Cretaceous in particular, with its warm oceans and high productivity, produced enormous quantities of organic matter that were buried and transformed into oil over millions of years. When we fill our gas tanks, we are, in a sense, tapping into the energy stored in the Mesozoic ocean. The shapes of the continents themselves are a legacy of the Mesozoic. The Atlantic Ocean, which began to open during this time, continues to widen today, pushing the Americas farther from Europe and Africa. The Indian Ocean, born as India rifted away from Gondwana, is still growing, and the Pacific, though shrinking, is still the largest ocean on Earth. The patterns of mountains, the locations of coastlines, the distribution of sedimentary basins, all were shaped by the tectonic forces that acted during the Mesozoic. And finally, there is the legacy in life itself. The creatures that survived the end Cretaceous extinction went on to evolve into the organisms we see today. The small mammals that scurried through the forests during the age of dinosaurs gave rise to the whales, seals, and manatees that populate today's oceans. The teleost fish that were just beginning to diversify in the Cretaceous became the dominant fish group, accounting for more than 95% of all fish species today. The corals that rebuilt their reefs after the extinction are the ancestors of the coral reefs we see in tropical seas, and the nautilus, the last surviving relative of the ammonites, still swims in the Pacific and Indian Oceans, a living link to a world that is long gone. The Mesozoic ocean shaped the world we live in today, not just geologically but biologically. The patterns of evolution, the distribution of species, the chemistry of the modern ocean, all bear the marks of that ancient sea. And by studying the fossils, the rocks, and the chemistry of the Mesozoic, we can better understand not just the past but the present and even the future. As we close this journey into the deep sea of the age of dinosaurs, it's worth pausing to reflect on what we've learned. This was an ocean unlike any we know today. It was warmer, from the surface to the abyss. It was higher, flooding across continents and creating vast, shallow seas. Its chemistry was different, with lower oxygen levels and occasional toxic dead zones. And its inhabitants were creatures both strange and familiar, from the spiral-shelled ammonites to the reptilian mosasaurs. But it was also an ocean that functioned in ways we can recognize. It had a food web, driven by photosynthesis at the surface. It had predators and prey, ecosystems and niches. It responded to changes in climate, in sea level, in the configuration of continents, and it left behind a record written in stone that we can read and interpret. The Mesozoic ocean reminds us that the Earth is a dynamic planet, constantly changing, constantly evolving. The oceans we know today are not oceans, permanent. They are just the latest chapter in a story that began billions of years ago and will continue for billions more. Sea levels will rise and fall, continents will drift, new ocean basins will open, and through it all life will adapt, evolve, and endure. And perhaps the most important lesson of the Mesozoic ocean is this: even in the face of catastrophe, even when conditions become extreme, life finds a way. The Oceanic Anoxic events, the asteroid impact, the mass extinctions, all were challenges that seemed insurmountable, yet life survived. It adapted, it rebuilt, and it went on to create the rich, diverse ecosystems we see today. The deep sea during the age of dinosaurs was a world of warmth and darkness, of abundance and danger, of life thriving in conditions that seem almost alien to us. But it was also a world that shaped our own, that left us a legacy in the rocks beneath our feet, in the oil that powers our cars, and in the living creatures that still swim in the ocean today. And so, as we step back from this journey, as we return to the present, we carry with us a deeper understanding of the ocean, of its history, and of its future. The Mesozoic seas are gone, but their echoes remain. In the limestone cliffs, in the fossils embedded in stone, in the very chemistry of the modern ocean. They are a reminder that the world is older and stranger than we often imagine, and that the stories written in stone are stories worth reading, worth remembering, and worth sharing. The deep sea during the age of dinosaurs was a place of wonders, a place where giant reptiles hunted in waters that covered lands now dry, where ammonites drifted through tropical seas, and where life flourished in an ocean that was warm from top to bottom. It is a world we can never visit, but through science, through careful study of the evidence left behind, we can glimpse what it was like. And in that glimpse, we find not just knowledge, but a sense of connection to the deep time that shaped everything we know. The ocean is still out there, still moving, still changing, and in a sense the story of the Mesozoic ocean is not over. It continues in the waters we see today, in the waves that crash on our shores, in the creatures that swim beneath them. The age of dinosaurs may be long gone, but the ocean endures, as it always has, and as it always will.